guys, thanks for coming back again for those that subscribe. If you are yet to subscribe, please click on the subscribe button and also on the bell beside it to notify you when we drop our new video. Thank you. Here we're going to look at radioactivity and what does radioactivity means. It is a spontaneous emission of radiation by an element. The word spontaneous in that definition simply means a action that can take place on its own accord. What do I mean by that? Bringing out an ice from a refrigerator, you need no force to keep the ice melting, so it will proceed on its own. Or placing a ball at the top of a hill, so you need no force or push to make the ball runs down the hill. So those are spontaneous processes. So radioactivity is also a spontaneous process. So that is why it is defined as the spontaneous emission of radiation by an element. And such element is referred to as radioactive element. What actually makes an element radiate? Actually, the atom of an element radiates is that the nucleus of such atom is unstable. The instability of the nucleus of an atom enhances the radiation. Are you following? So when radiation occurs, it's automatically known that the nucleus of an atom of such element is not stable. So, and in such states, they tend to disintegrate or decay, in the process of which they release radiation. And there are three major types of radiation that can be released from the nucleus of a radioactive isotopes or radioactive elements. So we have them to be the types of radiation. We have the gamma radiation, the alpha radiation, and the beta radiation. Let me represent them with their symbols. We have this for alpha radiation, or you call it alpha ray, or particles. They can be called alpha particles because sometimes they behave like a particle, so they are called alpha ray or particles. Then we have this to represent the beta ray or particles. Then we have the gamma ray. Gamma ray cannot be regarded as a particle. So the property of these three types of radiation are examined by passing them through an electrostatic field. So, and it was discovered that alpha ray was deflected towards the negative side, having the positive property. So while gamma ray went straight in the field without any deflection, then beta ray deflected towards the positive side, having the negative property. So let's get a diagram to explain that. If I have a source of radiation, if this is a photographic plate, then I have a source of radiation here. So on this we have the positive field, and here we have the negative field. So within here we have the electrostatic field. This source of radiation emitted three radiations, and one went straight, which is gamma radiation. Then the other one deflected towards the negative side, so this is alpha. And this deflected towards the positive side, so and that is beta. So this explains how the properties of the radiations. So from this property, we could predict that beta ray has a charge which is negative, is negatively charged. While alpha ray has it's positively charged. Then gamma rays has no charge, but the highest penetrating power. It has the highest penetrating power, so It is used for major some properties in the for sterilization, for surgical equipment, and so on. So, but however, we want to discuss these properties and when this radiation takes place in atom, what actually happens to that atom. So, for an unstable atom, when radiation takes place, they emit either of these three radiation or the combination of two or three of them could be emitted in a single radiation of atom. So in the process, something has happened, something already happened to the atom through which or from which the radiation were emitted. And what are the things? Because if an atom emits alpha particles are regarded to as the helium nuclei. Why? Because they have the mass number of 4 and the atomic number of 2. So meaning that if an atom loses alpha ray or alpha particles, then there will be reduction in its mass number by 4 and reduction in its atomic number by 2. Take for instance, this is radium 22688. If radium is a radioactive element anyway, so if it loses alpha particle, which can rather be written in this form as helium nuclei, due to the property of mass and atomic number it has, similar to that of helium, it produces alpha particles in the emission, then another element is being formed. When an atom radiates, atom of an element radiates, it doesn't remain that atom, it is converted to another atom. So suppose radium radiated, disintegrated or decay and releases alpha particles. So the new element that is going to be formed, element X, we have new mass of 2, 2, 2, which means there is deduction of 4 from the mass number and going to have 86 as the atomic number. That means there is reduction of 2 from the atomic number. And however, energy is released in the process. And a certain amount of energy is also released in the process of radiation. So that is one of the properties for alpha particles. So let's take into consideration beta particles. If an atom disintegrates in the process, releases beta particles, what happens to the atom itself? The atom do not lose any mass in the mass number, but instead there is addition of 1 to its atomic number. How? If radium 226 and 88 of atomic number loses 1 beta particle, this is it, there is addition of 1 to the atomic number of the new element formed. So then we are going to have 89. However, there is no deduction nor addition in the mass number side. And at the same time, energy is also released in the process. So this is the effects of alpha radiation and beta radiation on radioactive elements once they are emitted. So for gamma ray, they do not have any effect on the mass number or atomic number, either in form of addition or in form of reduction. They do not have any effect. They are emitted just like a ray from the nucleus of an unstable atom. So we have two types of radiation, radioactivity anyway, because there is a difference between radiation and radioactivity. So for the process of which a radioactive element emits radiation spontaneously is what we call radioactivity. So then the particle released in such process is what we call the radiation. So there are two types of radioactivity, sorry. So we have the artificial radioactivity is divided into artificial radioactivity, and we have the natural radioactivity. Let me explain this. In artificial radioactivity, okay, naturally we know that before an atom can radiate, definitely the nucleus of such atom must be unstable. So those radioactive isotopes that radiate spontaneously, naturally, is because their nucleus is unstable. So such element that radiates without any external effect is what undergoes natural radioactivity. But in some cases, there are some elements of which atom is not a radioactive atom. Some elements are not radioactive in nature, but we can still force them to radiate by bombarding them with neutrons or any other particles, preferably neutrons. So bombarding them with neutrons, bombarding the nucleus specifically with neutron, you make the nucleus unstable. So when you introduce nucleus and neutron to the nucleus of such atom, they become unstable. Once they become unstable, then there is tendency that they radiate. So in such process, we call it artificial radiation. So this is performed by an external body, like by an material equipment or machines that could be used to fire neutrons to the nucleus of a non-radioactive element, then making the what atom of such element radiate. So this process is artificial radiation. So, however, let's move straight away to half-life. Half-life. Now, the half-life of a radioactive element is the time taken for half of the whole atom of present in an element to completely radiate. For instance, I have an element containing about 600 atoms. These elements radiate in a series of processes, but the time taken for half of the whole atom present, which is 600, so half of it is going to be 300. The time taken for half of all these atoms present to completely disintegrate is what we call the half-life of such element. It's denoted by TR and also measured in seconds. However, we have some elements that their half-life is 10 years, 30 years, 100 years, and so on. And we have elements of which half-life is 1 minute, 2 seconds, 3 minutes, whatever. So the time taken for half of the whole element present, the whole atom present in an element to completely disintegrate is what we regard to as the half-life of such elements. So however, let's take an example based on what we have discussed earlier, this and the half-life, to see how it goes. There is a question that says a radioactive element X 35090 lost 3 alpha particles and 2 beta particles. What will be the mass and atomic number of the new elements formed, of the mass and atomic number of the new atom of another element formed, because that's we're emphasizing on the atom now. So this question says a radioactive element X of mass number 350, then atomic number of 90, lost 3 alpha particles and 2 beta particles. What will now be the new mass, that is the mass number, and the new atomic number of such elements? So we can write the nuclear equation for that. So, and that gives us, we have 350 and we have 90. it loses 3 alpha particles, which is helium nuclei, and loses 2 beta particles. And at the same time, don't forget, energy is released in the process. So, as it is, meaning that losing alpha particle here, you are going to reduce your mass number by 4, losing 1, and you reduce your atomic number by 2. So, meaning that 3 alpha particles, there will be loss in mass number by 3 times 4, which is 12 loss in mass number in the first place, then 3 times 2, and 6 loss in the atomic number. So meaning in the process of losing alpha particles, the 3 alpha particles, we are going to have 350 minus 12, then 90 minus 6 in the first phase. So at the same time, at the end of the day, we are going to have, that is 338 will be left in the mass number. Then 90 minus 6, we are going to have 84 left in the atomic number for the new element produced. However, the new element produced is not indicated here, so let's put it plus Y plus energy. So that's the first stage. So that means the new element here is a 338 in mass number and 84 in atomic number. So after the new element loses 2 beta particles, all to become Y. So losing 2 beta particles, there is no deduction in your mass number. So we can write this as 338 for the new element. Then, but there is addition of 1 to your atomic number. So since you lose 2 beta particles, there will be addition of 2 to it. So then this becomes 86. So that answers the question straight away. So therefore, the mass number of the new element of the new element Y will be 336. Then atomic number will be 86. That ends the question. So another question: a radioactive element of half-life 3 days contains 800 atoms. Anyway, the number of atoms present might be given, or sometimes it might be given the mass of the whole element. So still follow the same process. You can also calculate half-life with respect to the mass. So if considering the mass, if it is 800 grams, then the half-life will be the time taken for half of it, which is 400 grams, to completely disintegrate. So contains 800 atoms. How many atoms will be left after 9 days? This is a very simple question. Solution: how many atoms will be left after 9 days? And the half-life is 3. Don't forget that T half is 3 days. So, and the atom consists of 800 atoms. So, meaning that in the first stage of half-life, we can have, how many half-life is within the 9 days? We are going to have 3 half-life. So, definitely in the first stage, in 3 days, atom will be left to it. In first 3 days, which is half-life, so 1/2 times 800 atoms will be left, and that will give us 400 atoms. So in the first 3 days. So in the second 3 days, 1/4, that is half of half. So 1/4 times 800 will be left, and that will be 200 atoms. That's in the second 3 days. In third 3 days, all 3 days, we are going to have 1/8 times 800. It's because half of this is this, half of this is this. 1/8 of 800, which is going to give us 100 atoms. So after 9 days, which is 333, after 9 days, 100 atoms will be left in such elements. So that is how to a typical way of doing the calculation based on half-life. So, however, there is still one more thing we need to discuss on the half-life. So let's see. Which is the Decay's law. Decay's law. It was noticed that the number of the rate of disintegration, that means the rate of which atom of an element disintegrates, depends on the number of atoms present, is proportional to the number of atoms present. So from this idea, we can bring out a formula that can be generally useful in calculating the number of atoms that will be left after some time, provided we know the number of atoms present initially. So disintegration. So the number of atoms that disintegrates, or the rate at which those atoms disintegrate, is proportional to the number of atoms present. So that is Decay's law. So putting that into mathematical expression, we have the N dt. So this means rate of decay or disintegration. So if N naught represents number of atom present, then the rate of decay is proportional to the number of atoms present. So meaning we're going to have the N, the T is proportional to N naught. So meaning that the N, the T equals minus, we introduce a constant, N naught. The negative sign shows that the number of atoms decreases with time. So, and this constant we derive is called Decay's constant. Decay's constant. So where N naught represents, okay, the number of atoms present, then dN all over dt is called the rate of decay, or you call it the count rate. The count rate. So meaning that I can derive a formula for the decay's constant. So meaning that the decay's constant, the definition of decay constant, which is this, will now be dN dt negative with n times 1/n naught. So this is the formula for decay's constant. However, when we integrate these, we're going to get a reasonable formula of which we can use to determine the number of atoms present at a point of time, the number of atoms present at a point of time, and the number of atoms that will be left after a given time. So from there, if I have dN dt equals minus decay's constant of n naught, so crossing multiplying, we have dN equals minus this n naught dt. So dividing both sides by n naught, I'm going to have dN all over n naught equals minus lambda dt. So this is the same thing as 1 all over n naught dN equals minus lambda dt. So if I integrate both sides, integral of 1 over n naught dN with integral of minus lambda dt, taking the limit of this integral from n naught to n. So the lower limits represent the number of atoms present, while the n represents the number of atoms that will be left after a series of time. So integrating this, I'm going to have log E n knots. It's n, then n knots equals, then I have minus lambda t, because the integral goes with t. So from which I'm going to have log e into brackets n all over n knots equals minus lambda t. So bringing the e, I'm going to have n all over n knots equals e raised to power minus lambda t. So meaning n will be what? N knots dot e raised to power minus lambda t. So this formula could be used to determine the number of atoms left, which is n naught, provided we know the number of atoms present and we know the value of our decay constant. Then the time given to us. Okay, if I have 20 atoms initially, after 20 minutes, how many atoms will be left? Then we must know the value of our decay constant. However, can we proceed in finding a relationship between half-life and the decay constant? I think we can do that and we solve questions on this. If I have decided that at half-life, at that particular time when the number of atoms left will be half of the number of atoms that disintegrate. Take for instance, n represents number of atoms left. After time t, while n naught represents the number of atoms at a given period of time. So at half-life, at t half, it implies that the number of atoms left, n, will be equals to n naught all over 2. So at t half, that is at half-life, the n, that's the number of atoms that will be left, will be equals to half of the number of atoms present initially. So, sorry, not this. So from there, we can slot that into this formula and have n equals n naught over 2. So don't forget we have n equals n naught exponential minus lambda t. So this becomes n naught all over 2 equals n naught e raised to power minus lambda t. So from which this can go with this. So I have 1 over 2 equals exponential minus lambda t. So from which I have ln 1 over 2. That is, if e comes here, it becomes log e, then equals minus lambda t. So ln 1 over 2 is the same thing as minus 0.693 equals minus lambda t. So this goes with this. Dividing both sides. Don't forget this is at t half. So this t is going to be half-life. So making lambda the subject of the formula, so we're going to have 0.693 all over t half. And at the same time, this is the relationship between half-life and the decay constant. So meaning that in a question, if you're given to calculate the number of atoms that will be left, provided you know the number of atoms present, after a time that is not up to the half-life, provided you know the value of your decay constant, you can slot that here and get that completely. Even if the half-life of an element is 3 days, yet you can still calculate the number of atoms left after just a day, which is not up to the half-life, or after few minutes, which is not even up to 1/4 of the half-life. So using this principle, once you know the decay constant, you just slot it here. And if you want to know the number of atoms that will be left after 2, 3 minutes, 20 minutes, that will be your t. Then you will be able to calculate it using that formula. So let's look at questions that based on what we have just explained on half-life and decay constant. So the first question says the half-life of a radioactive element is 2 seconds. Find its decay constant. So very easy question. All we need to do is to make use of our formula that says the decays constant is equals to 0.693 over the half-life. So and that gives us, the half-life is 2. So meaning we're going to have 0.693 over 2, and that gives us 0.3 and 2 in 9. That gives us so the half-life now becomes 0.693 divided by 2, and that is 0.3465. The unit for decays constant is per seconds. So that is how to find the decays constant for that question. So another question says a piece of radioactive material contains 10 raised to the power 20 atoms. So if the half-life of the material is 2 seconds, the number of disintegration in the 4 seconds is, the number of disintegration in the 4 seconds is referring to the count rate. We're searching for the count rate. So don't forget the half-life T is equals to 20 seconds. Then we have the number of atoms, which is 20 atoms. Sorry, 10 raised to the power 20 atoms. So firstly, before we can find the n T, don't forget the n, the T is equals to minus the decays constant multiplied by n. So however, we don't have our decays constant. So to find that, we have which is 0.693 all over the half-life, which is 20. 0.349465, I mean 465 per second. So if this is the decays constant, then we can find the count rate, which is the number of disintegration in the first second. So and that will be equal to minus 0.03465 multiplied by 10 raised to the power minus 10 raised to the power 20. So and that gives us 3.465 times 10 raised to the power 18 negative. So this is the number of atoms disintegrated per second. That's the rate of disintegration. Thanks for watching. Please subscribe to our YouTube channel. It's free. Thank you.